the other doctors.
Okay, this is the time that I think we could start again. Actually, I don't know how can I introduce Dov Gabbay, but I have a conjecture that after 2000, in any published logic paper, you can find a reference to Dov, or one of its references has a reference to Dov. So please, Dov, start your talk.
Yeah, to start.
Yes.
Okay. So let me tell you about this lecture. This is the when I was looking at Ali's thesis, I thought it's very. I had an idea of how to salvage, strengthen standard deontic logic by means of what I will show you. I discussed it with them, and then I was invited. Ali asked me to give the lecture, so I had to make the slides very quickly. I couldn't even send it to Leon and Ali for comments. I finished them just now, and I'm going to talk about it, and we'll welcome your comments and participation if you like. This happened to me exactly 50 years ago when I arrived at Stanford as assistant professor in 1970, end of September 1970, and they asked me to give a lecture, a 2-hour lecture about stateability operator. Stateability operator, it means where you can construct in a grammar sentences that are correct but don't mean anything, like the house cut the bread with a knife. So what do you do with them? What kind of a modal operator? You say it's not stateable. So I started giving the lecture, and lo and behold, it wasn't only the graduate students. There was Hintika there, and Forrestal, and Patrick Supis, and all the heavies. So I said, look, I am showing you how to build the paper from scratch based on an idea. Right? If I get stuck, we'll backtrack and you can all participate. And it worked. And then it was even published. It's down here at the bottom, 1971. Okay? All right. Next. So what's the idea here? Standard deontic logic has problems. You have all kinds of paradoxes. So I thought, why don't we supplement it by means that can solve the problems? Because we have had all kind of papers in the literature. You saw this in the survey of Leon. They're all trying to solve, the way I see it, virtual movements that there is in the paradoxes. In Chisholm is after you go, you have a chance to tell or not to tell. With the minors, you move forward. Now you know where they are. Before you didn't know where they are. There's movement. So if I can put a connective, a non-connective, you don't invent, a connective that can do it, and be able, in this case, using linear logic to consume what I don't want, having passed forward, then we may have a very simple new standard deontic logic that will not have any problems, hopefully. So this is what I constructed. I'm not yet fully got comments from the other authors on how to do it. So let's start with tools. Tool number one is linear logic. So this gives you information about linear logic because we want to use it. So in linear logic, whenever you use a formula in modus ponens, you can't use it again. And then there is also, you've got to use everything that you have. Use all your resources exactly once. And this is for implication. So A implies B can prove B. You do one modus ponens. This is the assumption, and this is the ticket. And if you have A implies B, you can't get B. You don't have enough A's to do the job. Okay? Because this A, the minute you do modus ponens here, it's deleted. It's used. If you have too many A's, A and A implies B, you can't get again B because there remains an A which you haven't used. The beauty of this, that any logic can be turned into linear resource logic, because if you want to use more and more, just put more copies of it. Take any proof you do and put more copies of what you check. How many times have I used something? Put 5 copies if you used it 5 times. So it doesn't affect the proof theory, but it gives you an additional opportunity to use to get rid of things. All right? Now, Girard has a special connective called the additive. I don't know if I done the definition of it right, but it doesn't matter. We are constructing a logic. So this is what we want. A and B means you have as a resource A and B, you can take one of them and then finished. You delete. So this is a choice operator, really. Choose one, right? And think about the Chisholm, go or not to go. It's an independent choice. So here you have A and B, choose one. So if we have A and C, A arrow B, this can prove B because you choose the A. Don't choose the C, it won't work. Okay, once you've chosen the A, this goes, and you get the B, and all your resources are gone. Okay? First idea. I mean, this is an idea of linear logic. Nothing new. But now come a new idea. Next slide. And this is the clip linearity. Now, what is a clip linearity? What does linear logic do? Linear logic do, if you use something, junk it. That's it. Right? Think about cars. You have a new car. If you go to Saudi Arabia, you drive your Rolls Royce, it's full of sand. It gets sand into it. They don't bother. Junk it, buy a new one. So you can make a fortune going around in the desert looking for left abandoned Rolls Royces because they've got a sand in them. All right? But in real life, it doesn't work like this. When you buy a new car, there is the concept of a new car bought by businesses. They lease for 1 year and then get new lease on new cars. So the old cars used by business for 1 year, it's usually high mileage, but still a new status. You don't junk it. It is now comes as a new car by business. From a business. And families, I mean, that's the best thing to buy if you really want a big car, because the mileage doesn't matter, it's still good. All right? Then you use it for 2 more years. After 3 years, you must get rid of it because trouble comes. So this is another use, go to another state. Its value is clipped, right? And after 3 years, you give it to a student. That's it. Okay, so this is the idea of clip linearity. And we want to use it in clip linearity with the AND. So this is new to our paper in order to use in the new standard Deontic logic. And if you remember the AND in Ali's thesis and output 4 in input-output logic, I mean, it's the AND that is the problem. Okay? So this is A and B and C. You see, you have the inside parentheses the B and C. So if you use the A, you clip it, you don't abandon the whole thing, you clip it and have only B and C. All right? So here you have A and B and C, and A arrow B arrow X. This doesn't prove X in linear logic, but if you clip, then you can, because you will have here, you choose the A, from the A you get B arrow X, this remains, you choose the B, you get the X. And this one is abandoned because it doesn't have anything inside it, not another parenthesis. Okay? So I have to give you rules of how to clip, because this is how you do modus ponens with things like that. All right? Any comments so far? Everything is fine? All right. So I want to change notation because it will make it clearer. The A and B with a clip, write it like this. A comma B with a double parenthesis. Okay? So now I have to give you the rule. You have the double parenthesis, this one and this one. This is the entire set. You have A, B, but inside you also have things with parentheses. When you clip, these remain. So clipping this, which means you've used A or you chose B or you chose this, it doesn't matter. You throw everything out except the parentheses. So clipping this would give you the parentheses, just these. 1, 2. Okay? Now, think about it. When you have a tree, you can present it as sets, right? This is the first level, and then the parentheses, think of an inductive definition of a tree. This gives you the steps, but we'll see it later. Here, let's do this now. You have A and B and C, and A arrow B arrow X, and I ask, can I prove X? Choose A, and then we get B and C, because this has been used and it is clipped. This has been used and you have B arrow X, and you ask whether you have X. Choose B. When you clip this, there's nothing left. You get empty, and then you get X. All right? And what did I say here? Wait. Note, you clip only internal to AND. So clip A and B and C is B and C, this one, because this stays. All right? If you choose A. And clip A and B is empty because there's no parenthesis inside. Okay? If you want to keep the B, you have to put parentheses around it. Then it becomes an inner level. It won't get clipped. It's a better notation. In fact, it is a tree notation. Any questions? All right. Tool 1, tool 2. This is page 3 now. Page 3. Okay. Oh, I've done page 3. Page 4. Okay, let's look at the Chisholm paradox. You ought to go. If you go, you ought to tell. If you don't go, you ought to not tell, and you don't go. These are all independent. Two questions we have to pay attention to. One is, in the Chisholm paradox, you have not go, but maybe the guy decided not to tell. These are the facts. We must be able to treat all of that, because the not tell comes more internally as a fact. So pay attention to that. First, I am rewriting 2 and 3 as an additive, right? This means that you use only one of them. If you use one, you can't use the other. So how does the paradox go? I mean, you have not go, you got hotel. From 1 and 2, you got, you get O not tell. From 1 and 2, you get hotel. And then you got a difficulty. I mean, you can play on this different ways. All right? But if these two are additives, if you get, did anyone say anything? No. If you get O not tell, you can't use this one to get hotel because you can use only one. You see, if I were to come to you and say, use only one of them, you tell me this is a hack. There is a lot of ways of getting away from paradoxes. You look at the proof, you choose something there and say, don't use it, right? I don't like this. Many do that, but I don't like it. I mean, like going to the doctor, he says, every time I do this, my head hurts. And then the doctor says, then don't do it, right? That's not a way of dealing with it. But here, the additive is in linear logic. I didn't invent it. And it's very useful in computer science. It makes sense. It has applications. Fine, I'm using something that has a different meaning as well. I'm using it here. And then the clip also has, I'm using things that make sense, right? Can be applied further. All right. So if we choose 3 and get O not tell, then 2 is not available. But there is another bit of a problem. If we choose 2, go, what we get is O go is there. Go and hotel are supposed to get hotel, but and not go. Somehow it's not completely symmetrical. So I'm allowed to help a bit, making it symmetrical. I don't have to do it, but it, okay. So V is for violation. Okay. I think that if we allow for variation, and I don't know how to do it yet, but if we use it wisely, we may, as we go along, if V is not consumed, which means you can have as many copies of it as you want. We can even count the number of variations as we prove in the system. So let's try this one. And then this morning when I started, well, I got up at 3 o'clock in the morning working on the slides. I thought I'll replace A with a choice modality. But I think we can have the O because the choice is being done already with the clip, with the and. So I added this comment. I don't think we need to replace O. And then it will look nice. You keep the standard Deontic logic. You just turn it into linear logic by adding as many copies as you want so that the proofs will go through. And instead of deleting, in this case, of the additive, you use the clip. And then some of them you can delete, some of them you can't delete. You adjust it by going through all the paradoxes and see how it goes. And well, we have the know-how between all of us. I mean, we can carry on. You take the idea and you push it through and see what happens to it. Okay. So let me write. I wrote here the paradox is. You see, here is either you violate or you don't violate the go. Okay. If you go, then either you tell or you don't tell. If you not go, either you tell or you don't tell. And then you have a choice, violate or not violate. All right? I mean, this is fine. You have a choice to violate or not. If you violate, you don't go. If you don't violate, you go. And then again, you go. It's exactly meaning the same. All right? except I am embedding it in a different logic. And I think you don't need this C. You can just write it direct. That's why I said you can keep the O. Don't use it. Use it for other things. All right, next. So now we have to construct a logic with the AND. All right, so you have multi-sets. The V, this means you can use as many copies as the V as you want. Maybe we don't need that. We just say the V is not deleted when used. And we have to decide later. And then you have, this is a modality. And the modality can do modus ponens with a thing like that. This is a additive. It has all the x's in here. This says x, choice of x, or modal x. This has x implies AI. This has modalities, several of them. I equals 1, 2, 3. They are all the things that start with x. These are all the rest of them that will never get clipped. Okay? So if you have something like, if you go, you tell. If you don't go, you don't tell. If you tell, you fax. If you don't tell, you don't fax. If you fax, you phone. I mean, you can carry this on for as long as you want. So you have a long chain. You'll have lots of embedded these one inside the other, and they can clip as you go along. All right. So now what you do, you choose the AI because they start with the X, and you clip, you get only these, the embedded AND. So here is the embedded AND, and you consume that. In other words, if you can't use it again because now you've gone forward. And here's some more axioms. If you have several of these, you have several of the X's here, then you get what's the inside. You get your choice. These are the AIs because these are consumed. The AIs get in here, and this is what's left in here. And you carry on the proof with this. This is the next level, right? So you really have. I think I wrote it in the next slide. Where is it? So here I really should say, if you have additive of A and B, you either make a choice or you say, if I were to choose A, what do I get? If you to choose B, what do I get? Get rid of the additive A and B and put in the consequence additive A and B. So if A gives A prime and B gives B prime, then A and B additive gives A prime and B prime additive. You just carry on. And you need this rule because suppose you have a fact of not tell. You can't use it yet. So it stays there and you use it when it comes up the front in the proof theory. Any questions? Okay, we carry on. Now, the minus paradox is really, oh, here it is. You get it at the top. The minus paradox is very easy to solve because you have not, don't block both of them. If in A you block A, in B you block B, and in A or in B. If you just use it like this, 1 and 2 are conjunction, you get block A or block B. Okay? But that's not. You use these two as an additive, so you choose one of them. This means in the next step, you know which one, and that's the one you choose, and then you don't have a problem. I think this is directly solved this way. Next. Now I want to show you what really happens here. Let's do a graph of what's S is for start. So if you violate, you go to not go. If you don't violate, you go to go. And here again, you not violate, you tell. You violate, you not tell. You see, this is the progression. Start, step 1, step 2, step 3. When you use the and, the additive, and put one inside the other, you're building the tree, but this time axiomatically. It's no longer semantics. I mean, this is not semantics. This is a description, a graphical description of what the embedded additives do and what the clip does. The clip does is when you violate or not violate, you take the go and not go, a choice, additive, and the rest, these are the rest of the tree, remain, and these go out. Oh, okay, you move forward. And in linear logic, they also use graphs, proof nets, and all kinds of things there. In fact, the graphs are more expressive. We don't need that. All right. So here is a more complicated. Just a minute, I'm moving very fast. No, oh, half an hour. That's all right. This is a more complicated example where you can have facts, and so it's longer and longer. So I wrote it down, and here we have this. You should go. If you go, you tell. If you don't go, you don't tell. If you tell, you fax. If you don't tell, you don't fax, and you fax. Okay? Because they're all independent. So this guy just faxes. All right? But when you have the fax and you want to start here, you can't, because it doesn't fit anything. So I've given you a rule. Just a minute. What did I write? I put a comment there. Where's the comment? Oh, I lost the comment. You need a, okay, let me go here. If you have this X here and there is no X in here, there's a Y, you don't do anything. In order to clip and do a modus ponens with this in a way, the X must be in and then you take the AI. So when you get to here and you have the facts will not affect anything here until it comes to the front. In this case, tell will. If he told, then the tell would have come to the front, but the fax is at the end, so it's his last choice, but it doesn't interfere. Okay, so here is the structure of it. You have not V and V. V violate, not go, and not violate gives you go. And then this is internal, which has two internals. And this is also internal, which has two internals. So the whole tree is formalized using additives. And the modus ponens advances you. That's exactly the right proof theory. But it is proof theory of linear logic with a clip, which is also a good idea. Why do you have to throw it away? I mean, clip it. Okay? So it's linear logic with a clip. Okay. Now we reach the conclusion. Linear logic generalizes any logic because any proof can be made linear by adding more copies as needed. So we are losing nothing. So I say take SDL, add the additives, and add the clip. You can leave the O, why not? And then adjust as needed by way of going over all the major paradoxes and see what's happening to them. Try to solve and see what's left and see whether, right? And this I already explained, that you advance in the violations by using the clip linearity on the additives. Now, when you turn it into a logic, you can make more of it. You can take Boolean expressions like P and Q, P and not Q, not P and Q, not P and not Q. For each one of them, you say what you want. It's a more complex choice. Put them as additives. I mean, the fact that you have only one atom each time, the machinery works. And then you get more. You get a wider tree there. Okay? And then we can look at cycles. We can look, I mean, this is, what would be the semantics of this? Right? If we leave the O, we want Boolean semantics. This is what Ali did. So we can give Boolean semantics to this, because after all, this says that linear logic is the same as any other logic. You have Boolean semantics of multisets. Or I think we can do possible world semantics, because the layers, now you look at this as possible world semantics, and you move through the accessibility relations. And this way you can model the clip. I think we get a very nice logic here. Okay, that's it. That's as far as we've got.
Many thanks, Dov, for your nice idea. Actually, I have a lot of questions because I think this is something new.